Good morning, Year 6, and it is Wednesday the 3rd of March, and today we're going to be looking at calculating the interior angles of polygons. So as you can see from the title there, we need to first explore what interior angles mean and also what the word polygon means as a refresher for you. And then we need to be knowing about how many degrees there are within different sided shapes, different polygons, and we will look at the formula to calculate these also. So hopefully by this point you will have completed your arithmetic practice, and then you can go straight into the lesson and we will get on as soon as possible. So firstly, the question about this word interior angles. So the angles below, you can see, have got on them marked some of the interior angles. So I wonder if you could pause the video and have a think about what those interior angles might be, and what that interior, the word interior, actually means. So there is lots of information. Actually, we've got here 3 isosceles triangles, and these 3 isosceles triangles have been given different marks in them, and we have got, you can see there are some lines here on each of the triangles, and there's one line marked, and this indicates that these 2 sides of this triangle are equal in length. So you've got one here and here, so these 2 sides are equal in length, as are these 2 sides here. And that tells us that it's an isosceles triangle, because isosceles triangles have 2 sides which are equal in length. And also a property of an isosceles triangle is that they have 2 angles which are the same. So you can see that here we've got 48 and 48, and we've got our 30 and 30. Obviously, if all the angles were the same, all the sides are the same, we'd be looking at an equilateral triangle. But for this case, we've got only 2 sides are the same and 2 angles are the same. So we're talking about an isosceles triangle. We're not talking about a right angle triangle. There's no right angles in these triangles. And we're also not talking about a scalene triangle, which refers to the fact that there is no sides the same length or no angles which are the same. So hopefully with that little bit of information and extra knowledge, you have identified where the interior angles are within these 3 isosceles triangles. And these are these numbers here that indicates the degrees measurement of the angles, which are inside these closed shape, these closed polygons. Polygon, we're going to be talking about the meaning of that in a moment, but these are the interior angles for a closed shape. And you can find interior angles not just on triangles, but all kinds of closed shapes in the same way. So that's what we're talking about when we're talking about interior angles. And tomorrow we'll be looking at some exterior angles. So you can see here just a little mention of what we're going to be looking at tomorrow. So you've got your interior angles inside that closed shape, and you've got your exterior angles outside of them. So the different colours there marking the exterior and interior angles. So with that term kind of clarified for you, we can now move on to the next term, which is all about what a polygon is. So a polygon, the word poly is meaning many, so it's a many-sided shape, and these are straight sides. So when we're talking about polygons, we're talking about 2-dimensional plane shapes that have straight sides. So you get examples of these: triangles, rectangles, pentagons. They can be regular or irregular. The important feature of polygons are that they have straight sides to them. So any shape that has a curved side is not a polygon, like a circle that we're quite familiar with, and some of these other maybe more unfamiliar shapes. If it's got a curved side to it, it is not a polygon, but if it's got a straight side, we are talking about polygons. And I'll try to keep using that language throughout the lesson. So Year 6, we're going to have a look in which we can prove how many degrees there are in the interior angles of various shapes. And we're going to look at the triangle and, well, any quadrilateral actually. Doesn't have to be a square, but a four-sided shape, and just prove to ourselves that actually we can use this help sheet that Mr. Gunn has provided for us, so that we can know that all the interior angles of these shapes do add up to that total within the middle. So we're going to check that he's been providing us with the correct information. So in order to do this, I'm going to ask you to see if you can get yourself a triangle. You will need to make sure your triangle has straight sides, so it's not got any curves to it, so it's a polygon. And we're going to watch a little video now so you can see what it should look like, and might want to follow along the steps as you do it. But what you're going to be doing once you've created your triangle is you're going to be cutting off the angles, cutting off the corners of your triangle, and then rearranging them and together along a line. Okay, so what you'll need to do is you'll need to label, as you can see, the various corners on your triangle and your angles, and then cut off, as we've just talked through, the different angles, the different corners of your shape. And then you need to rearrange them together along a straight line. Hopefully you'll see this able to work. Give you a chance to do that. And you will probably start to recognize and see that actually they do fit together along a straight line. You can almost provide yourself with an extra additional tool and put a ruler there so you can check that you're along that straight line and it's really nice and straight. Okay, and just make those fit in exactly as you want them to. So hopefully by that short demonstration, you have been able to recognize that when you are thinking about putting your shapes, your angles, along a straight line, you can use them to create this straight line and therefore see how much the total interior angles total up to. And we know something about angles along the straight line from our lessons on the beginning of this week. And we know that on a straight line, all the angles will add up to 180 degrees. So this is a way of proving that a triangle's interior angles also total up to 180 degrees as given on your help sheet, so we can know that the interior angles of a triangle are 180 degrees. And this works for any triangle, whether it be regular or irregular. And you've probably created your own irregular triangle, whether it be isosceles, even a scaling. You might have even been lucky to try and create yourself an equilateral triangle if you were being particularly accurate, or you might have had a right angle triangle. Whatever the case, as in the video, you can cut off those corners, cut off those angles, and rearrange them to be able to make a straight line. So proving that within a triangle, within a three-sided polygon, the total number of the interior angles is 180 degrees. You can see on this demonstration that actually at either whatever corner I'm dragging, whatever vertices I am touching upon and changing, the total of the interior angles is always going to be the same. It's always going to be 180 degrees, and that is always the case with any type of triangle. So whatever vertices I'm moving, vertex I'm moving, you can see that is still the case. Okay, so if we now go back and do the similar investigation, but this time we're going to be thinking a little bit about a quadrilateral. So what I'd like you to do with this quadrilateral, and you must make sure you've got straight sides to your quadrilateral, you're going to cut off the corners, the vertices, and the angles from your quadrilateral, and you're going to see what you can make using these angles. So I gave you a bit of a tip in the triangle, but have a go with this quadrilateral. So make yourself a quadrilateral, any four-sided shape, cut off the vertices, cut off the corners, cut off those angles and reconstruct them to see what you can make. See? So in this case, we haven't labeled it with the letters. We've just got numbers there for each of the vertices, for each of the angles that we're talking about. And you can see it being very slowly rearranged into, well, you might have had the same success, into a circle format there, circle shape. So all these angles are around a point. And so that should be starting to ring bells already, total up to 360. So that is a way of just proving to you that the interior angles of any quadrilateral are going to be adding up to the total 360. So it just proves the information that we've been given on our help sheet. So this is just the starting building block as a pictorial representation, if you like, of how we can know that there are 180 degrees in every triangle. Now we know that obviously when it's coming to equilateral triangles and regular shapes that the angles are the same, but we know that every shape, whether it's irregular or regular, the interior angles will still add up to the same as over here. So three-sided shapes, three-sided polygons will add up to the interior angles being 180, and four-sided, well, quadrilaterals, polygons, will always have the total interior angles being 360, five-sided for 540, and six-sided 720, etc., and so on. So it doesn't matter whether they're irregular or regular, that still applies. So today, one of the first activities you're going to be asked to do is look at the interior angles of regular shapes. And just to clarify and remind you that when we're talking about regular polygons, regular shapes, we are talking about shapes that have the same length sides and the same angle, all the angles are the same inside them. So on your help sheet today, which you have hopefully got with you, you have got some of this information given to you already. So you can be referring to that to help you solve these calculation problems. So you can see that in an equilateral triangle, all the interior angles total up to 180 degrees. And we're going to explore that a little bit further in a moment. And in a square, where all the sides are equal, obviously, all the angles total up to 360. As for a regular pentagon, 540, regular hexagon, 720, regular heptagon, 900, and a regular octagon, 1080. So that's the total of all of the interior angles added together. And if we're thinking about regular shapes, or we're trying to find out how many degrees in total the interior angles total up to, there is a formula that we can use. So this formula is on your help sheet, and it sort of has two stages to it. One that's useful for all polygons, whether they be regular or irregular, and the second part of the equation that you've been given will help you with this formula to find out the degrees that each of the angles are in regular shapes. So this is the formula. You don't necessarily need to worry about this today because you'll have your help sheet to refer to. But if you're in a position and don't have access to the help sheet and you wanted to calculate how many degrees in total the interior angles would calculate up to, then this is a way in which you can do it. So there's almost a step 1 and step 2 to this. So if we have a look at this equation, if we look at the top of it, this piece of information here will give us, for any shape, we can use this bit of the formula to work out what the total of the interior angles will be. So if I look back at our pentagon, we actually do know the answer to this, but we can sort of use that to work backwards, if you like, so you can see how how this formula can be used. So if we start with our 100, oh, let me change the colour so you can see quite clearly. So we've got our 180, and we're going to be timesing it by n take away 2. And you will have noticed on the formula, there's a little code here that says that n equals the number of sides that we are referring to. So in this case, we're referring to 5 sides because we're talking about a pentagon. So I'm going to put my 5 there. And when we're talking about how we calculate this, we are going to be thinking about the use of BODMAS. Now, if you remember from BODMAS, we're starting with our brackets first, and then we're going to be doing our multiplication afterwards. Because we've got, so we have got here, if we write this out, we've got 180, and we are going to be, we've already done this brackets, this calculation within the brackets. So 5 take away 2 is 3. And that will give us the number of degrees that are in the total of all the interior angles of a pentagon added up together. Okay, so we've already found for this shape. Now I can apply this to any shape, this formula. So if I was thinking about a 11-sided shape, I could use that to unpick how many degrees in total there would be of the interior angles of that shape. And then if we're thinking now the second stage of our working, and we're looking at wanting to, oops, let's get a different color, might help us. We're thinking about the second stage and we're wanting to look at a regular polygon of that shape. So this is only applies to regular shapes. Then for the regular shapes, we can then use our total, and our total in this case being 540 degrees, and we are going to divide that 540 by the number of sides. And so in this case we're talking about 5 in our pentagon, so that n represents the number of sides, 5. And then we can do our 540 divided by 5, and that will give us what one of the angles in this regular pentagon will be, one of the interior angles will measure. And obviously we can apply that because 180 would be the same on every angle within a regular pentagon. So this formula, part of the formula here, really refers to all the way we can find out the interior angles of all polygons, and this will help us find out one angle within a regular shape. So there's a difference between that. So obviously today you're at the advantage because you have some of the information about regular shapes on your help sheet. So you may not need to do any of these formula calculations, but there's just an extra bit of knowledge for you there. So we can apply this information into this regular hexagon here. So as you can see, I have got regular hexagon, and I know that for a couple of reasons. I know that because there are 8 sides. I know it is regular because this mark here indicates, and you can see it all around each of the sides, indicates that each length of each of these sides is equal to each other. And also you can see, and you might be able to just spatially see that all of these angles are also the same, they're all equal, and that all points to the fact that this is a regular shape. So we know it's an octagon, it's got 8 sides, but if we didn't have our help sheet and we wanted to find out the total of all the interior angles, we would need to do some calculating using our formula. So we know we start with our formula, we've got 180 degrees, and we're going to times that, sorry, not degrees, 180, and we're going to times that by the number of sides. And in this case, we've got our n, so in this case it's 8 subtract 2, and that will give us the total of all of the interior angles added together. So if we make this broken down, we've got 6 here, so we're actually doing 180 times by 6. There we go. and that will give us 1080, which is the interior angles of a octagon added all together. 1080 degrees. I've made a mistake there. So our whole interior angles of an octagon are 1080 degrees. And then if we wanted to find out on this regular, underline that loads of times, on this regular octagon, what each of these angles would be, we would need to divide that by the number of sides. So I'll try and put that in another colour. So our number of sides we know that is 8. And so then we will be doing the calculation, which is 1080 divided by 8. I'm going to do that using short division here, so you can see how that might be done. I'm just writing that out. So we can't get our 8 into 1, so we've got nothing there. Put this across here. So how many 8s in 10? Well, it goes in once with 2 remaining. How many 8s are there in 28? Well, there are actually 3. 8 times 3 is 24, and we're left over with 4 remaining. How many 8s are there in 40? Well, there are actually 5. Which is nice, works out nicely. And then we can go back to our bar model here, and we can place in that it's 135 degrees, as will be each of the angles, because as we have already identified, this is a regular octagon, that will continue there. So each of these angles on our regular octagon are 135 degrees. And we could check that by, if we times that by 8, we would get back to our total number here, which is the total number of the interior angles within this regular octagon. So how can we use all of this information that we've gained about interior angles to calculate the missing angles on this shape and some other ones that you will be asked to do today in your task? So a little bit like the angles along the straight line, angles around a point, we've been given some information, and actually we know some more information about interior angles as well that will help us approach this problem. So we know we're talking about the interior angles. We know we're talking about the angles inside this closed polygon. We are looking at what our missing angle is. We know something already about this shape because we know this is a triangle shape. And this triangle shape is, we know it's a triangle because it's got 3 sides. And we know something about all the angles, interior angles, what they total on a 3-sided shape. And as we've already explored, we know that the total interior angles on a triangle is 380 degrees. We also know that these are 2 angles already known to us. So we've got our 38-degree acute angle there. And we already have information about our obtuse angle, 123 degrees here. So we've already got lots of the information that we need. We are looking for this missing angle and working out what that could be using the information that we have been given. So, and the first thing that we need to do is find out what we know so far. So far, we know that with these 2 angles that are known to us, 123 plus 38, we have got 161 degrees of interior angles already known to us. So with that information, we can move straight on to working out what our missing angle is in a similar way to we've been thinking about angles along a straight line earlier on in the week. So if we now do 180 degrees and we're going to subtract what we already know is our 161 degrees, we will see what we are left with, our missing angle, which is actually in fact 19 degrees. So we can start filling that information into the diagram, into our bar model and into the diagram. And then we can check that we have indeed found the correct missing angle here, because if we were to add together our amounts, so we've got 123 here, plus our 38, plus our 19 that we've just uncovered. Sorry, no, it's a bit funny there. This will get us back to our total of 180 degrees, which is the sum total of the interior angles of a triangle. Now we can use some further knowledge about our knowledge of quadrilaterals and also our knowledge of some of the missing angle work that we've done previously. So if we have a look here, you can see that we're dealing with a quadrilateral, we're dealing with interior angles, so the angles within this closed polygon. We know it's a polygon because it's got straight sides. So we already know that if it's a quadrilateral, the interior angles will total 360. So we can put that as our whole that we know, because the interior angles will in total up to 360 degrees. We know some information already about the angles within this shape. So we already know we've got 75 degrees, and we know, so that's our angle there. And we also know that we have got our 70-degree angle. We haven't got any number information here, but hopefully you will remember from our learning earlier in the week what this symbol tells us, and that says that we've got a right angle on this shape. So therefore this will be a 90-degree angle here, which we can add to our bar model of information. And obviously we are still trying to find out what our final missing angle is going to be. So we don't know that one yet. So similar to before, really, we're going to be finding out firstly what we know, and then find out what we are left with that will be our missing angle, because we already know this information that all the interior angles of a quadrilateral will always add up to 360, and we had a go at proving that a little bit earlier on. 235 degrees are known to us, and therefore we can then work out the missing angle. So if we do 360 and we subtract 235, we will arrive at our missing angle. Our missing angle in this case is 125 degrees. So we can put that missing angle back into our bar model. That will therefore give us a chance to check if we added all these parts, would it make our whole 360 degrees? And obviously add that back into our diagram, because we now know what that missing angle is, that X that was there. Okay, so hopefully that will help you start to unpick all the things that you need to do in your maths session today. As always, the answers will be found at the bottom of your sheet, and the help sheets are invaluable in trying to locate the information that you need to be able to be successful at the learning today. So once you've done your mathematics for today, please send it into your class teacher so that we can see the work you've been up to. So goodbye for now.